Go ahead.
So thanks everyone for coming to the last session of this morning. The session is on cryptanalysis, and the first work is on the tightness of the suffix key sponge bond. And it is a work by Christophe de Bruynich and Bart Bennick, and Bart will give the talk.
Okay, thanks for the introduction. Yes, just to be clear, this was accepted before I was the program chair. So I didn't just accept my own work. So tightness of the suffix key sponge bound. One of the most efficient ways, I think, to build a MAC function or a PRF is the full state keyed sponge. So the idea is that you take a b-bit permutation P, and you can initialize the state with the key and possibly also an IV if you need to, or a nonce. And then you permute, you get a secret state, and then you absorb b bits at a time. It's very efficient because you compress with the state of the primitive. On the downside, you don't get any mode level protection against side channel attacks. The reason is basically that if you have here, you have a secret, the permutation evaluated on the key, and the attacker has kind of full power in manipulating the state by adding a state, a plain text over the b bit. So it's extremely efficient, but it also kind of doesn't give mode level protection. So if you implement it, you need to be careful with your implementation. And this attack actually allows differential power analysis. One way to solve this is this famous approach, which I think stems back to the Goldwasser-Mikali approach. The idea is that you start with a secret key, and then you can take an IV or a nonce or something like this, where you look at the first bit of the nonce, if it's a 0 or a 1, and based on that, you can proceed on the tree. If it's a 0, you evaluate the block cipher or primitive based on input of the key and the encoding of a 0, otherwise you encrypt it or process it with the encoding of 1. And you can go on like this bit by bit until at the end, you end up with an output, a state, which you can then use to work with further. And this will always be different or independent, at least, because you always have a different path in this tree, depending on the IV. So you can turn this also into a sponge. And this is an approach introduced by Taha and Chaumont in 2014. It also appears in the ISAP. It kind of appears in the ISAP approach with some variation. The idea is that we take a nonce, and this nonce, you process 1 bit at a time. So you don't absorb over the entire state, but only 1 bit at a time. And this way, the attacker has less freedom in manipulating the static secret here. We actually, a couple of years back, 3 years back, we proved leakage resilience of the duplex construction. And this can be seen as a duplex construction. So the leakage resilience of this one follows from the analysis we did in 2019. The downside is that you need a nonce. So how else can we efficiently do a leakage resilient or a function that's easier to protect against leakage? And one way is the famous hash and PRF approach. So you have a message of arbitrary size P, you hash it, then you get a digits of, in this case, 2K bits, and only then you start doing some secret stuff. So then you incorporate the secret key. You have this function G. So the only thing you need to protect here in the implementation is the function G. You don't need to do a protected implementation necessarily of H, because H cannot leak the key, obviously. The downside is that you have a 2K bit input here, because otherwise you can have collisions faster than the birth than the security level. Now we can kind of turn this into the sponge, and we end up with SUX. And SUX is a suffix keyed sponge bound, which was already proposed before in the sponge formalization, but in the general form, in the description of ISAP by de Bruynich et al. 2017, the idea is that we take the normal sponge with R-bit absorption. So we cannot do full state absorption, but R-bit absorption is still very good. And only then you absorb the key using some function G. It doesn't need to have 2K bits here, but just K bit input, because we use the inner part and we make one more permutation call and then we get the tag. And this function is leakage resilient if G and the last call are sufficiently protected. That's what we proved a couple of years back. In the black box model, G can be an XOR actually. So you can do it very efficient. You can just XOR the key there and then you're done. In more detail, we proved the bound of this form. We assumed that G is 2 to the minus delta uniform, 2 to the minus epsilon universal. Typically, this means that G behaves sufficiently good, but an XOR satisfies this. So an XOR satisfies this for the minimum of delta and epsilon is K. But you can also take a PRF or in general a hard to invert function there. And we proved there are 3 terms. The first one is obvious. This is just inner collisions in the hash part, because if the attacker finds just a hash, inner collision in the hash part, the security is gone. And then we have 2 other terms that involve a mu. And this mu, it scares a little bit, but it's quite intuitive in some sense. So here we see, for instance, mu subscript t. Forget about the other numbers here. This means that it is a maximum size of the multi-collision on t bits. So it's very likely that there will never be a multi-collision of larger than t elements, except with a small probability. So this is the bound we proved 3 years back. And now we actually analyzed this bound from the tightness perspective. So we considered, is this bound tight? Now for the first term, well, it's not surprising. Inner collisions on the hash part, then security is gone, obviously. Then we looked at the second and the third bounds. Because we have this multi-collision term, it's not clear what this actually means. Is this just an artifact of the proof, or can we actually break it? And we looked at 2 different settings. So one of them is where we simply take the XOR as G. So the key is just XORed into the state. And we describe 2 attacks. So one of the attacks actually does a multi-collisions on the tag. Basically, it matches the third term, multi-collisions on the tag. And then we recover the key. We managed to recover the key. And the other one is a multi-collision in the second term, for the second term. It basically corresponds to a multi-collision attack at the place of the key, and we recover the key. Okay, so if we take a simple to invert function G, you can break it up to this bound, so the bound is tight. And as a third attack, we consider the case where you have a PRF as G. This really corresponds to the case what we see in ISAP, in the NIST finalist ISAP. And there we also find a multi-collision based attack that matches the second term. Obviously, it's not a key recovery attack, but it is a forgery attack. The third term is basically independent of this function G. So the original attack kind of showed tightness. Now, this is a 5-minute presentation. I'm not going to discuss the actual attacks, but in the slides, in the full slides, they are explained in detail, and also in the paper, they are explained with analysis. So if you're interested, just look at the full presentation or the paper. Okay, so thank you for your attention.
So thank you, Bart. Is there any quick questions? No. So I have a quick one. It's on the fact that your G and where the key arrives has the same impact on the rate part and not on the over part of the state. Would be give something better if you can provide add some key also in the last part of the capacity, or doesn't matter at all?
For the proof. So if you also add the key to the bottom part, but then you're evaluating the function twice. So I don't know how this works with leakage, but it doesn't. I don't think it improves the bound, but I'm not 100% sure. I think the bound won't get any better than this. Okay.
Okay, so let's thank the speaker again. Okay, so the next talk of the session is on quantum period finding is compression robust. It's a work by Alexander May and Lars Schlieper, and Lars will give the talk.
So, hello. Today we have only access to a few hundred qubits, physical qubits that are also quite noisy and not capable of performing most of our known quantum algorithms today. And furthermore, we don't have access to a single logical qubit that is noiseless and on which most of our cryptographic quantum algorithms rely on. However, there are many companies like IBM, IonQ, and SQC that announced to build quantum computers capable of having some millions of qubits in the next 10 years, and are also capable of simulating or creating some hundreds logical qubits. Our goal in this work was to make more efficiently use of this few available qubits in the future in terms of period finding algorithms. From this, we will result into quantum computers and quantum attacks be sooner available and so sooner a threat to our security, which will also lead to the fact that we have less time to prepare for the quantum attackers. For this, we primarily study SIME problem, which is a problem giving access to a 2-to-1 function with a period S to find this period S. This problem is classically hard to solve and requires expected at least exponentially many queries to the function. But however, with quantum access to the function and 2n qubits, this problem can be solved in polynomial time on a quantum computer. This can be done via SIME's algorithm, which uses a circuit like this one here to sample randomly y's that are orthogonal to the hidden period S, and then afterwards computing S out of this sampled y's. Thereby, it takes n qubits for the input, where the y's is later encoded in, and n qubits to hold the function volume. Let us have a closer look on the distribution of this y's. Normally, in SIME's algorithm, these y's are uniform distributed over all y's that are orthogonal to S. Here, for example, for n equals to 3 and S equals to 0, 0, 1. We see that we measure the probability to measure any y that is non-orthogonal to S is 0. Note that the 0 vector don't give us any information about the S. In our work, we now tried to reduce the number of qubits that we need to encode the function value f by used hashed versions of the function to 1 bit. By this, we changed the distribution of the y's. This can look like this, for example, for a hash function. We see a bias towards the 0 vector, as well that we maybe can't measure any some vectors anymore. But fortunately, we don't measure any false vectors that are non-orthogonal to S. This is only one hash function. If we look at different hash functions, we see also other patterns occur. Like for some hash functions, the probability for some y's are even higher as before. By taking the average over all hash functions that maps to 1 bit, we get a distribution like this, where the probability over the choice of the hash functions for the 0 vector increased roughly by 1/2, and every other probability decreased roughly by a factor of 2. This means also that we only need roughly the double number of measurements with these hashed versions to solve the same problems, whereby we only require roughly half the qubits amount, since we only require 1 qubit to encode the function value. Furthermore, we have shown that we can combine our technique with other techniques like the Grover-Mead-Sime technique and the offline Sime technique, which further reduce the number of qubits that are required by a factor for some cases of 4, and makes our technique even more easier to implement. Additionally, we have shown that this technique is not only limited to Simon's algorithm, but can also be applied to a broader range of period finding algorithm, including Shor's algorithm. And we conjecture that in most cases, a single hash function, simply like a bit projection, is enough. To summarize our results in the light of security, quantum algorithms may be earlier and with fewer qubits a threat to our security, and we should prepare faster. Thank you for your attention.
So thank you, Lars, for the talk. Is there any question for Lars?
The question is if I have any ideas over the complexity of the hash function. So the hash function itself can be implemented quite easily. For example, we can use the scalar product as hash function that could be implemented with one Toffoli gate that can be implemented in place with roughly linear many gates, linear depths with quadratic many gates. But with a simple bit projection, we could also use only a simple C0 to use it. In the case that we combine it with the Grover time or offline time technique. In the other case where we don't have this additional space, so we have directly to use the hashed oracle. There are some technical problems that can be circumvented if we have special implementation of the oracle.
Okay, thanks a lot. Is there any questions? Quick questions? No. So if not, let's thank Lars again. Okay, so the third talk of the session will be a week quiz for the Craft block cipher. It's a work by Gregor Leander and Shahram Razulzadeh, and Shahram will give the talk.
Okay. Thank you for the introduction. Craft is a tweakable block cipher with a block and tweak size of 64 bits, and the key is 128 bits. And it is claimed that it provides 128-bit security in the related tweak model. It follows SPN structure with 32 rounds that the 31st ones are identical up to tweaky and round constant addition, and the last one is just a linear round. And it is very similar to Midori and skinny block ciphers, but the main difference with them in Craft, all the round operations are involutives. So the inverse of the round operations are same as themselves. Considering this matrix of nibbles as the input for the round function, it starts with mixed column operation that a linear mapping from lower half is added to the upper half. And then round constant is added to fourth and fifth nibble. And third operation is just addition of the round tweaky to all of the state. And the last linear operation is permutation of nibbles. That using a permutation P, it changes the position of the nibbles. And note that any nibble from lower half will go to the upper half, and also the same, the vice versa. So any nibble from upper half will go to the lower half.
And the last operation is just applying an involutive Sbox to each nibble. About its round 3-key schedule, it is very simple. The 128-bit keys split into two parts, K0 and K1, and it also compute a updated tweak that Qn of t. So that is a nibble permuted version of the tweak. And by XORing K0 or K1 with T or updated T, it provides 4 round 2 keys, and then just iterate them for the rounds. Overall, Craft provides decryption same as the encryption up to a modification on the round 2 keys and reversing order of the round constants. First and main contribution of our paper is to show an equivalent representation for Craft, and then show how it is possible to change it to a weak to key model with a Feistel network. It starts with here we show 2 consecutive rounds of the cipher, that the left branches for the upper half and right branches for the lower half. The first one is the mixed column prime, that the linear mapping which lower half is added to the upper half. We show it with mixed column prime, and then we split at round 3 key and Sbox layer to 2 parts, and the last one is just permutation of nibbles. Note that this Pn prime and Pn double prime are the shuffle in the nibbles for each half, and then of course there is a swap. And since this permutation of nibbles altogether is involutive, it caused that Pn prime and Pn double prime to be inverse of each other. It is possible to bring these 2 operations, Sp prime and Pn prime, from end of each round to the beginning of the next round. So like this in this figure. And it is again possible to bring these 2 operations to inside of the bridging branch and also after the bridging point. So it will be like this structure. And since we can replace position of Sp prime and Pn double prime with each other, and this Pn prime and Pn double prime are inverse of each other, they can be removed just by modifying this Tk double prime. So it will be like this. And as you see, this is the new representation for Craft block cipher. And it is very similar to Feistel network, but there's a difference, and that is in the case for Feistel network, this operation doesn't exist, and it is always the ident function. We showed that this keyed operation will be the same as the ident function if and only if that this tweaky be equal to 0. Repeating this to every round, we will have the weak tweaky structure of the Craft block cipher that follows the network Feistel network, and it is only possible that the the key is one of the 2 to the 88 weak keys, and if the used tweak is one of the 256 tweaks, weak tweaks corresponding to that used key. This weak tweak key structure can be used, can be analyzed against common attacks for block ciphers, but we only did it for differential analysis. I'm not going to talk about their details. If you are interested, please have a look on the recorded video or read the paper, please. About the results, we present a 230 round single tweak differential attack with complexity of 2 to the 94 encryptions and 2 to the 72 data using 2 to the 51 blocks of memory. We also did a 206 206 rounds related to differential attack on craft. But the complexity for this one is higher, and it is 2 to the 105 encryptions and 2 to the 73 data using to the 60 blocks of memory. Thanks for your attention.
Thanks, Shaham. Is there questions for Shaham? So I have one. So you have this new representation, and it seems there is many properties of the rounds of craft that made this new representation possible. But did you try to identify more general behavior of the linear layer? Because I assume it's from the linear layer that you can do this representation. Do you have ideas of properties on the linear layer that you can pass from SPN to Feistel representations?
I would say it's not only the linear layer, but also the Sbox, because Sbox is involutive. This can also be applied to Skinny, but for Skinny, this Sbox is not involutive. So both linear layer together with Sbox helped us to change from SPN to Feistel. And that's not, for example, possible to Skinny. I hope this answers your question.
Yes, thanks, thanks a lot. So let's join me to thank Shaham again. Okay, so the next talk of the session is about maximums of the additive differential probability of exclusive OR. And it's a work by Niki Moua, Nikolai Kolomek, Danil Akhtiamov, Ivan Suturman, Matvey Panferov, Ksenia Titova, Tatiana Bonish, Evgenia Ishkukova, Natalia Tokareva, and Bulat Jantulikov. And Niki will give the talk.
Thank you, Jan. I was wondering if you're going to say all the names. So maybe I should explain why exactly there are so many authors here. What happened was that in 2020, right when the pandemic started and summer came, I got a request from people at Novosibirsk State University who were organizing a workshop in a similar style of, we used to have these eCrypt research retreats or ASK in Asia, for people who still remember those. So the idea was, give us a problem to work on, and then we'll put ourselves together in teams with a lot of students who are just starting out to see if we can maybe solve this problem. Okay, so I have my box of problems that are still interesting to look at, I think, and that haven't been solved yet. So this is a problem that I'll talk about that is more than 10 years old, that I've been working on it. And every time that I gave this problem to somebody, they found it interesting to look at, like get some new structures, see some ideas, and explore a bit the basics of cryptanalysis. But it has never been a solvable problem. So that's good for me, because then every time people are asking me for a problem, I can just give the same problem again. But what happened here is 2 months after the research retreat was over, I got an email saying, oh, we solved it. So that's why I'm here to present the result. It's about differential cryptanalysis, but it's going to be super easy. So at least to explain the problem, not actually to solve it. So let me recall here, as you've seen in many of the presentations before, the idea behind differential cryptanalysis.
So you have an input, you have an output, and what happens if you flip some bit or bits at the input? You want to know what's going to happen to the output. It's maybe going to have some bits different as well, but which bits it is depends on some random choices. So there's some probability involved here. And typically what we'll do is we want to look at differences in the middle so that we can get a good estimate of what the probability would be to go from a certain input to a certain output. Now, we're not going to look at a full cipher. We're actually only going to look at one operation, one XOR operation. So it's going to be much, much simpler because we're going to look at addition, rotation, XOR type constructions. The XOR is the one we're going to analyze with differences that are additive. Now, easier might be to look at the other way around, and that's maybe a result that is more common in papers when people want to analyze these ARX constructions. So you might say, my differences are XOR differences. That means I'm flipping bits, and I'm trying to see how those bits propagate. And then we'd like to know, let's say the operation is an addition, otherwise the propagation is always for rotation for XOR probability 1. And there's a paper by Lipma, Wallen, and Dumas at FSC 2004 that shows that you can represent this probability by multiplying a set of matrices. What you need to do is just see like what matrix, what difference do I have at what position? Like here it says, for the word on the left, there is, for the right one, right? There is a difference. And then for the word on the right, because you have two inputs for your addition, there's no difference. There's also no difference on the output for this bit position. So you select matrix A, 1, 0, 0. So here are the matrices, you multiply these and you get probability. There is the dual of this. You can say, what if my operation is the XOR and my differences are additive differences? Then you can apply a similar approach as well, but the matrices happen to be a bit bigger. But it's again the same idea. So you are going to look at what differences you have at every position. You multiply these matrices based on the difference that you have, and that gives you the probability. So this is the probability, differential probability of the XOR operation when your differences are additive. Here is the unsolved problem, right? The theorem. So in this paper of Lipma, Wallen, and Dumas, 2004, there is a theorem that says for all gamma, if you want to maximize over alpha and beta, then the maximum probability is going to be the one for which you have difference 0 gamma going to gamma. It says in the paper, the proof is omitted from the conference version. And actually reaching out to the main author, it turns out that the proof has been lost. This seems something that shouldn't be so difficult. Actually, the paper says it's a surprisingly easy result, but we don't know how to do it, and it doesn't turn out to be so simple. At least all the attempts over the past more than 10 years to try to recreate this proof have failed. Now, I mean, even if this was a full-length presentation, to go through the whole proof, because there are many cases and it gets a bit technical, is something I'd never be able to do. So I'm just going to give you very briefly, running out of time anyway, this main idea of how the proof works. I'll go through a few of the extra results, because actually on the way to the result, there are a few other things that we've seen, and then conclude the paper. So one thing I want to point out here is that while it is a proof, you could just say, let's assume that it's true because it's true on small word sizes. But that's something that doesn't necessarily hold, because sometimes some conjectures can have very large counterexamples. You can also say, well, I only care about a specific input difference and I want to know the maximum output difference. But then you can also not get there, because we want to look at a result that holds generally for any value of the bit size, because that's the idea of the proof. So there were briefly some observations that are explained in the full version of the presentation and also in the slides that I'm going to skip, that lead up to a sketch of the proof. And it's basically a proof that is done by induction. So if you are going to assume that it holds for n equal to 1, and then you suppose that it holds for a value of n, the proof shows through a detailed analysis of cases that it also holds for n plus 1. So here, I'm quickly going over these results. There are some symmetries that you need, because you might want to look at not just what is the maximum does this theorem hold, but what are the specific values of gamma that maximizes it? You might look at how to compute these types of probabilities, and there are some strategies here that can be interesting as well. I definitely want to include this slide because one of the reviewers said, whoa, that's a really nice formula. So here's a nice generalized Fibonacci style sequence that you can find that appears in analysis of these types of constructions. So I'd like to conclude here. What we do is we provide in the paper the missing proof of this theorem 3 of Littmau, Wallen, and Dumas 2004. Also showed you which are the gammas, very briefly, that satisfy this value, how to compute them. There are more efficient ways of doing that. And this minimum non-zero probability is one thing that I quickly skipped over. So let me finish my talk here. If there are any questions, I'd be happy to answer them.
Hi, I have a question here from the Zoom. Jan, do you hear me? So
yeah, Jan is here.
Yes, I'm hearing you.
Good. So here's a question of Kevin McKelvey from the Zoom. Kevin asks, what is your new unsolved problem that you give to people? So you solved the problem from the 2004 paper. So Kevin suggests that you give some new problem.
Okay, so I see Kevin had 2 questions, right? The first question of Kevin was the comment, oh, I think Fermat tried that, say the proof doesn't fit in the margin. So here, there was actually part of the proof or maybe something else in the source code comments of the LaTeX file, but not something that could lead to actually something you could use it. So instead of just saying the proof didn't fit in the margins, now we could say maybe the proof is in the source code comments. What's the new problem I'm giving people? Well, I think it's important to see what people's background is. This is a problem that I think engineers might not care too much about because you could just assume it's true and your day is over, right? But I think mathematicians really appreciate that you shouldn't be making all these assumptions, but you want to check exactly what is going on and what is how you want to analyze and get a precise result. So Kevin, let me know which types of problems you're looking for, more mathematical, more applied, types of things you like to explore more, and I'll have a problem just for you and we'll present it at FSC 23 in Beijing. How about that?
That sounds good. Maybe I'll add another question. If you want to maximize your probability over gamma as well, so is it just the Hamming weight of gamma that the least Hamming weight it has, the more will be the probability, or you can say something more interesting?
No, so I'll give a very brief answer because we're running a bit out of time. We tried all of the basic techniques to solve this and they all fail, and the proof is actually quite a bit technical. So all of the attempts that try to see if there's maybe an easy way of explaining this seem to have failed. There is perhaps an easier way of doing it because the paper says it should be surprisingly simple, but what we described in the paper is the easiest that we came up with is maybe still a bit involved.
Mm-hmm. Okay, good, thanks.
Okay, so let's thank Nikki again. Okay, so the next talk is about proving resistance against infinitely long subspace trails, how to choose a linear layer. And it's a work by Lorenzo Grassi, Christian Rechberger, and Markus Schaffnegger. And Markus will give the talk.
Yeah, so thanks for the introduction. This will be about partial SPN ciphers or permutations and their linear layers. So let's start. What's the motivation behind this? Well, recently we've seen some partial SPN or partial SPN-like schemes, and they are mainly tailored towards various use cases. So for example, we've heard about them, zero knowledge use cases, also multi-party computation, where we try to have some optimal number of multiplications, for example. And some of them are, for example, so Hades, Mimsy, or Poseidon, and similar versions Starcut. But there was a problem with those, and namely, some of the proposed instances had some weak linear layers, which actually allowed to attack a large number of rounds. And this was shown in a crypto paper 2 years ago, and also in the Eurocrypt paper from last year. However, in these papers, these results were only for some particular matrices which were used in these two constructions, or in these three constructions above. So the question we tried to answer in this paper was, how do we guarantee security in general? And we did this by analyzing the linear layers of these constructions with respect to subspace trails. So what is a subspace trail? I will not go over this definition in detail, but let us just assume that we have a set of subspaces here, use, and if they fulfill this relation for a particular round function R, then we say that this set here is an R-round subspace trail for this round function R. And if all the U's here are the same, these subspaces, then we say the trail is invariant. And what we focus on in this paper are trails which are infinitely long. So there's also the notion of iterative subspace trail. I will not go into that now. You can see in the full presentation. Why do we care about the subspace trails? Well, they're very closely related to truncated differentials with probability 1. And we have here a partial SPN scheme, we have here a partial nonlinear layer. And for example, by using the analysis, we can ensure that any linear layer, so this is the affine layer, which has some linear, so some matrix in there, we can ensure that essentially we avoid the situation where we have a zero difference at every input of the Sbox for an infinite number of rounds. So our paper tried to solve this problem, so we can now choose some linear layer which prevents this property. And this also works for more Sboxes. All right, so we had two cases. We considered both inactive and also active Sboxes. So let me start with the inactive Sbox case. Here we see a classical round function of some partial SPN. So the Sbox is applied to the first word, and then we have some matrix multiplication, and then we have some round constant, or round key addition. And we work over a prime field here. And for example, if we choose some input subspace, which is generated by an eigenvector of this matrix here, then you can also see that there's a zero here, so the Sbox is not activated in the first word. So essentially, if we have some element of this subspace and we apply this round function, then the result will also be an element of the subspace, and we can do this an infinite number of times, and it will always be a result, so an element of the subspace. So more generally, if we have some input subspace which does not activate any Sboxes, so which has these zeros at these Sbox positions, and which is M-invariant, so which doesn't change via the linear layer or via the matrix multiplication, then this IS generates an infinite long invariant subspace trail. And the thing for iterative trails is similar. We just use an exponent here for the matrix. And yeah, now you may wonder, how do we actually find those M-invariant subspaces? Well, you have to see the full presentation for that. So the second case we consider are active Sboxes. And here we'll only go over the very intuitive approach. So we know that active Sboxes must not change the space or the subspace. So what do? Well, we first ensure that every inactive Sbox is actually inactive via a condition. And the second condition is that if an Sbox is actually active, then the space generated by the single unit vector at its position has to be fully included in the initial subspace. So what this means, maybe more intuitively, is that if the Sbox is applied, so it's active, and so the output difference can be anything, but it doesn't really change the subspace because any difference is included in the initial subspace then. Yeah, and if those two conditions hold, then the active Sboxes do not change the initial subspace. So let me also give some practical results. Here we focus on prime fields, and we tested both random invertible matrices and also random MDS Cauchy matrices. And we see, for example, that if we have a rather small field size, so here only 4 bits for this red column here, then the percentage of a matrix or the probability of a matrix to be vulnerable is rather high. But then if we increase the bit size, the field size, then the probability gets lower. And of course, so this includes all the trails we analyze in the paper and to up to some fixed period for the iterative trails. So let me conclude with a sufficient condition and also with a short summary. So all the subspace trails we discuss in the papers need these M-invariant subspaces. So as a designer, we can guarantee that no such subspaces exist. And this is possible with the following theorem, which basically, which is based on minimal polynomials of the linear layer up to some period again, which is chosen before. And yeah, so this is only a sufficient condition, which means that there are some secret matrices which do not fulfill it. And yeah, it's a very easy check compared to the algorithms we have. And yeah, the proof is also in the paper. So as a summary, we determined some conditions for the security of linear layers in partial SBN constructions. We consider both prime fields and also binary fields and both inactive Sboxes and also active Sboxes. More details on the full paper. This includes the proofs, the algorithms, and also some tools. So for example, you can put in a linear layer and it tells you if it's vulnerable or not. And if it's vulnerable, it even tells you the initial subspace, which makes it vulnerable. And let me also mention that differential attacks are not the only concern. So for example, if we have such a subspace, we can exploit in algebraic attacks the fact that the degree grows much slower or basically starts growing after a certain number of rounds, because in the first rounds, we don't have a degree growth here on all the rounds, essentially. Yeah, and so the results let us fix some potential issues with both Hades MIMC and also Poseidon and Starcut. Thank you for your attention.
Okay, thanks, Marcus, for the nice talk. Is there any questions for Marcus?
Maybe I can have one question. So Marcus, you spoke about two cases. First, where there are no active Sboxes, and the second, when there are active Sboxes. Do we have any interesting example, say, in an existing cipher, where the second case occurs? So you have an active Sbox, and nevertheless, you have some meaningful characteristic of this form?
So thank you for the question. So we did not analyze any ciphers beyond those mentioned, also because there are very few who which actually fulfill these conditions and work over larger fields and so on. But we have some concrete examples also in the paper where, so for example, for constructions or for linear layers, which are vulnerable only to active Sboxes, or when there are active Sboxes, but not when there are inactive Sboxes. So that's certainly possible. And yeah.
Okay, good. Thanks.
Okay, any one more quick questions? So if no, let's thank Marcus again. So it's time for the last talk of this session. Okay, so the last talk of the session is about cryptanalysis of the So Dark cipher for HF radio automatic link establishment. And the talk, it's a work by Marcus Donsarier, and Marcus will give the talk.
Hello, everyone. My talk here describes the cryptanalysis of a cipher called So Dark. And it's specified in two American standards, one federal standard and one military standard, as well as in a NATO standardization agreement. It's used to encrypt so-called linking messages between high-frequency radios in automatic link establishment networks. And despite the fact that this cipher has been in active use for almost 3 decades now, there appears to be no previous cryptanalysis of it. And that's the primary motivation for this work. So in short, the So Dark cipher algorithm is meant to encrypt 24-bit words in ALE. So it's therefore a 24-bit block cipher. that uses a 56-bit key and a 64-bit tweak. In second generation ALE, which is the version most commonly used still today, the cipher has 8 rounds. And the round function is illustrated by this slide here. The lowercase A, B, and C are the round key bytes, and each round key byte is formed from 1 key byte and 1 tweak byte. And the key and tweak bytes are simply used in succession. So in the first round, bytes 1, 2, and 3 are used, and in the second, 4, 5, and 6, and so on. This means that in every round, only 24 bits of key and 24 bits of tweak are used. The 3 output bytes of each round are then dependent on 2 or 3 bytes of the previous round, as well as only 1 round key bytes. And yeah, that's probably the critical weakness of the cipher, that it's the attacks presented in the paper all sort of start out on with an attack on a round reduced version of the cipher with 6 rounds. And we consider cases where we have plain text ciphertext tweak tuples, where the differences between the tweaks in pairs are only in the 5th tweak byte. So the other 7 tweak bytes are identical. And this actually turns out to be a very, very common case in the real world application of this cipher. Practically every transmission will have these tweak differences. And then if we discover a pair of these tuples where the ciphertexts are identical, we can, using only the round function definition, actually calculate part of the difference after the 3rd round of the cipher. And knowing this difference after the 3rd round, we can then check for it given the plain texts by iterating over only 6 of the 7 key bytes. This can be trivially extended to 7 rounds by selecting ciphertext pairs with a different difference than the collision in the 6-round version. This is no longer possible in the 8-round version. However, we can identify pairs that have a probability of having this collision, and more importantly, we can reject pairs that have a 0 probability of having this collision. And in doing this filtering, we also gain information about one of the key bytes, which turns out to actually reduce the time complexity compared to the attacks on 6 and 7 rounds. The 8-round attack can also be adapted into a chosen ciphertext attack, where we, by generating 256 plain text ciphertext tweak pairs, can guarantee that one of those generated pairs will cause the required collision for the attacks described here. And this then in turn enables chosen ciphertext attack with very low data complexity. Here's a summary of the attacks presented in the paper. And as you can see, all the attacks have low data and time complexities, which means that they are possible to implement on a personal computer. And this has been verified experimentally, and I have implemented both the attacks as well as brute force implementation in C and in CUDA. And they have been used to verify that this works, and we've found that it's about 170 times faster than brute force. Yeah, and that concludes my talk. Thank you.
Is there any question for Marcus?
Thank you for the talk. I have many questions, but probably I will wait for your long version. Just by curiosity, so you said it was only 56 and was your plan to reduce. So I don't understand why didn't anyone say that it has to be like rejected? Do you have an answer for this, or do you...
Yeah, I'll start by repeating the question. So the question is, the cipher only has a 56-bit key, so why is it still used, and why hasn't someone decided to change it? And I could probably talk about this for an hour. The short answer is, in I think one of the standards, one of the later versions, there's a mention that there's been, quote, concerns about the security of the cipher. And in the latest version of the standard, there's a proposed replacement for this. But as far as I know, the replacement isn't in use anywhere.
Okay, maybe any questions from...
Is there more like this? More ciphers that we
The question is, are there more ciphers like this? And yeah, probably. We just need to figure out how to find them.
So we also have time for one quick questions, maybe from people that are online, because we also have many time us with Marcus, I think this afternoon. No,
So there are no questions here in the online.
Okay, so I think we can finish the session of this morning. We are exactly on time, and that's time for lunch. And this afternoon there is 2 workshops, so that means 4 presentations, all on